From time to time, we all ask some deep and difficult questions. Why is the world filled with woe? How can we make it better? How do we give meaning and purpose to our lives? Well, as difficult as these questions are, many people have answers to them. For example, some people believe that morality is dictated by God in Holy Scriptures. When everyone obeys His laws, the world will be perfect. Or, problems are the fault of evil people who must be shamed, punished, and defeated. Or, our tribe should claim its rightful greatness under the control of a strong leader who embodies its authentic virtue. Or, in the past, we lived in a state of order and harmony until alien forces brought on decadence and degeneration. We must restore the society to its golden age. Well, what about the rest of us? In Enlightenment Now, I argue that there is an alternative system of beliefs and values, namely the ideals of the Enlightenment, that we can use knowledge to enhance human flourishing. Many people embrace the ideals of the Enlightenment without being able to name or describe them. They've faded into the background as the status quo or the establishment. Other ideologies have passionate advocates, and I suggest that Enlightenment ideals too need a positive defense and an explicit commitment, and that is what I've tried to do. The ideals of the Enlightenment, I suggest, can be captured in 4 key ideas: reason, science, humanism, and progress. Let me say a few words about each. It all begins with reason, with the realization that traditional sources of belief are generators of delusion. Faith, revelation, tradition, authority, charisma, mysticism, intuition, the hermeneutic parsing of sacred texts are all ways of being wrong. Reason, in contrast, is non-negotiable. As soon as you try to provide reasons why we should trust anything other than reason, as soon as you try to suggest that you are right, that other people should believe you, that you're not lying or full of crap, you've lost the argument because you've appealed to reason. Now, humans on their own are not particularly reasonable. Cognitive psychologists, most notably Amos Tversky and Daniel Kahneman, have shown that human beings are likely liable to generalize from anecdotes, to reason from stereotypes, we all seek evidence that confirms our beliefs and blow off evidence that disconfirms them, and we're overconfident about our knowledge, our wisdom, and our rectitude. However, people are capable of reason if they establish certain norms and institutions, such as free speech. Anyone can criticize the claims of anyone else, such as open criticism and debate, logical analysis, fact-checking, and empirical testing, which brings me to the second of the Enlightenment ideals, science. Science is based on the conviction that the world is intelligible, that we can understand the world by formulating possible explanations and testing them against reality. Science has shown itself to be the most reliable way of understanding the world, including ourselves. An important Enlightenment ideal is that there can be a science of human nature, and that beliefs about society are testable, just like any other beliefs about the world. Now, science provides not just technical know-how and handy gadgets, but fundamental insights about the human condition. Naturalism. The universe has no goal or purpose related to human welfare, with the implication that if we want to improve that welfare, we've got to figure out how to do it ourselves. Entropy. In a closed system, one without input of energy, disorder increases. Things fall apart, stuff happens. And that's because there are vastly more ways for things to go wrong than to go right. Evolution. Humans are products of a competitive process which selects for reproductive success, not for well-being. As Immanuel Kant put it, out of the crooked timber of humanity, no truly straight thing can be built. This leads to the third Enlightenment theme, humanism, that the ultimate moral purpose is to reduce the suffering and enhance the flourishing of human beings and other sentient creatures. Now, that sounds pretty obvious. Who could be against human flourishing? And the answer is there are lots of alternative moral systems that prioritize other things, such as that the ultimate good is to enhance the glory of the tribe, the nation, the race, the class, or the faith, to obey the dictates of a divinity and pressure others to do the same, to achieve feats of heroic greatness, or to advance some mystical force, dialectic struggle, or pursuit of a utopian or messianic age. Humanism is feasible because humans are endowed with a sense of sympathy, another recurring Enlightenment theme. That is, we can be concerned with the welfare of others. We feel others' pain. By default, our circle of sympathy is rather puny. We tend to sympathize only with genetic relatives, with close friends and allies, with cute little fuzzy baby animals, and that's about it. But our sense of sympathy can be expanded through the forces of cosmopolitanism, through education, journalism, art, mobility, and reason. I can't insist that my interests are special just because I'm me and you're not, and hope for you to take me seriously. So when we're engaged in discourse, that forces us to expand our circle of sympathy to include others. The final Enlightenment ideal is progress, that if we apply knowledge and sympathy to reduce suffering and enhance flourishing, we can gradually succeed. Now, if human nature doesn't change, how could progress be possible? And an important answer from the Enlightenment is it's possible through benevolent norms and institutions, by which we can deploy energy and knowledge to combat entropy. We can magnify the better angels of our nature, such as reason and sympathy, while marginalizing our inner demons, our biases, our illusions, our tribalism, our dominance, our vengeance. Examples of Enlightenment institutions, brainchildren of the Enlightenment, are democracy, declarations of rights, markets, organizations for global cooperation, and institutions of truth-seeking, such as academies, scientific societies, and a free press. So, how did that Enlightenment thing work out? Well, if you ask most intellectuals, the answer is not very well, because I have learned that most intellectuals hate progress. And intellectuals who call themselves progressive really hate progress. If you think we can solve problems, I have been told, then you have a blind faith and a quasi-religious belief in the outmoded superstition of the false promise of the myth of the onward march of inevitable progress. You are a cheerleader for vulgar American can-doism, with the rah-rah spirit of boardroom ideology, Silicon Valley, and the Chamber of Commerce. You are a practitioner of Whig history, a naive optimist, a Pollyanna, and of course a Pangloss, an allusion to the Voltaire character who declared all is for the best in the best of all possible worlds. Now, by today's standards, Pangloss would be categorized as a pessimist, because a real optimist would think that we can do much better than the world we find today. This is definitely not the best of all possible worlds. But the case for progress should not depend on an attitude, a temperament, whether you have a sunny disposition. It can be treated as an empirical hypothesis. Human well-being can be measured. We can measure life, health, sustenance, prosperity, peace, freedom, safety, knowledge, leisure, happiness. I submit, if they have increased over time, that is progress. Now, in Enlightenment Now, I try to make the case with graphs plotting measures of human well-being over time. Because of the constraints of this room, although I feel naked telling this story without graphs behind me, I'll have to do a combination of verbal description and pantomime to convey the same point. Well, let's begin with the most precious resource of all, life itself. Through most of human history, life expectancy at birth was around 30 years. But thanks to vaccination, sanitation, antibiotics, and other advances in health and medicine, life expectancy at birth today in the developed world is greater than 80 years, and in the world as a whole, 71 years. And virtually no one guesses that it is that high. Through most of history, the biggest hit to human lifespan has been child mortality. Indeed, even in a country as wealthy and advanced as Sweden, 200 years ago, about 1/3 of children did not make it to their 5th birthday. Today, in the poorest parts of the world, no more than 6% of children fail to make it to their 5th birthday. This would be sub-Saharan countries like Ethiopia, which just in the last 40 years have brought their rate of child mortality down from 25% to 6%. Still too high, but the improvement is continuing. Maternal mortality is another contributor to premature death, and in Sweden 200 years ago 1% of mothers died in childbirth. That has been brought down now to 1/3 of 1% in the poorest countries of the world. And with most of the measures of well-being, unfortunately I can't depict it in graphs, but the general pattern that you see in measure after measure is that before the Enlightenment, about 250 years ago, pretty much everyone was wretched. There was universal poverty and hunger and early death. European and American countries were the first to make the great escape from universal poverty and early death, followed, though, recently by Asia, Southern Asia, and now Sub-Saharan Africa is closing the gap. Health. As someone who has spent a good chunk of his career studying the grammar of the past tense in English, I can identify my favorite past tense sentence in the history of the language. And it comes from a Wikipedia entry for smallpox, and the entry begins, "Smallpox was a disease caused by two viruses." Yes, the definition is in the past tense because smallpox, which killed some 300 million people in the 20th century alone, has ceased to exist. And similar progress has been made, well, not quite similar yet, but other diseases are slated for the past tense, including polio and guinea worm, and even diseases that will not be extinguished are all coming down in the mortality rates: pneumonia, diarrhea, malaria, measles, HIV/AIDS. Sustenance. Starting with the agricultural revolution in Britain in the late 18th century, with crop rotation, other advances in agronomy, later synthetic fertilizers, the mechanization of farming, selective breeding as captured in the Green Revolution, thought to have saved 1 billion lives, and transportation networks, the number of calories available per person has increased in every part of the world, including sub-Saharan Africa and India. Now, this would be a dubious form of progress if all those extra calories were just making fat people fatter. But in fact, undernourishment is being decimated. In 1947, approximately 50% of the world met the definition of undernourishment. That fell to about 33% in 1970, and it has come down in every part of the world. It's effectively zero in the developed world, but also coming down in Latin America, Asia, and sub-Saharan Africa. As a result, famine, which was one of the horsemen of the apocalypse, which could strike any continent without warning for most of human history, has pretty much been banished except for the most remote and war-torn corners of the world. Prosperity. For most of human history, economic growth pretty much was non-existent. A tiny little increase until the Industrial Revolution in the 18th century, which initiated a blast-off of exponential growth, with the result that gross world product increased about 200-fold in the last 250 years. Once again, this was an uneven process. It began with Europe and the Americas, thanks to the growth of education and technology and institutions that foster commerce and trade. But Again, this would be a dubious achievement if it simply made rich people richer again. But in a development that's seldom appreciated, the growth of prosperity is starting to put an end to extreme poverty. Extreme poverty is standardly defined as the minimum amount necessary to feed oneself and one's family. By that criterion, 200 years ago, about 90% of the world's population fit the definition of extreme poverty. That has now fallen to less than 10%, and the United Nations has set as one of its Sustainable Development Goals the elimination of extreme poverty everywhere on Earth by the 2030s. May we all live to see that day. As a result of the decimation of extreme poverty, global inequality has been decreasing. Now, it's inevitable that with the Industrial Revolution and the first expansion of wealth that inequality must have increased, because before the Industrial Revolution, everyone lived in squalid poverty, pretty much. With the discovery of new sources of wealth from industrialization, it meant that some people escaped from extreme poverty, leaving others behind, therefore increasing global inequality. But more recently, because of globalization and trade and markets, poor countries have been getting richer faster than rich countries have been getting richer, and the global inequality index has been decreasing. Now, of course, within wealthy countries, like the United States and Britain, inequality has been increasing. But perhaps what's more relevant is not so much the gap between the rich and poor, but the situation of the poor. Not so much whether everyone has the same, but whether everyone has enough. And in a revolution that is seldom appreciated, there's been a massive expansion in the amount of social spending, that is, reallocation of wealth to the poor, the sick, the young, the old, in every developed country. It's even has a name called Wagner's Law. For most of history, even the wealthiest countries devoted perhaps 1% of their GDP to social spending. Today, the median is 22% of social spending. Even a country like the United States, which is behind the Western average, allocates 19% of its GDP to social transfers. Thanks to these social transfers, while inequality has increased, poverty has not. By the measure of disposable income, that is, after taxes and transfers, the poverty rate in the United States has fallen by one measure from about 30% in 1960 to about 6% today. And if it's measured by consumption, by what people can afford in food and clothing and shelter, the poverty rate today is less than 3%. Peace. For most of modern history, war is the natural state of international relations, and peace was a mere interlude between wars. I have a graph from a previous book, The Better Angels of Our Nature, Why Violence Has Declined, which shows the percentage of years that the great powers of the day, the major states and empires, were at each other's throats in major wars. And it goes from about 100% in the 16th century to 0% today. There has not been a great power war directly pitting two great powers against each other since the United States faced off against China 60 years ago. If we zoom in on the post-war period, we see that another unheralded development, which is, with ups and downs, the global rate of death in warfare has been dramatically decreasing. During the era of the Korean War, about 20 per 100,000 people per year died in war. That went down to about 9 or 10 in the 1960s during the Vietnam War, about 5 in the 1980s during the Iran-Iraq War and the Soviet invasion of Afghanistan. Today, even with the worst war in a generation, the Syrian civil war, it's about 1.2. With the signing of the peace agreement between the government of Colombia and the FARC guerrillas, the last war in the Western Hemisphere came to an end. So we're living in an era in which an entire hemisphere is free of war. And indeed, 5/6 of the world's surface is now free of war. Freedom and rights. Despite obvious backsliding in Russia, in Turkey, in Venezuela, and just today in China, the overall trend towards democratization has not been reversed. The world has never been more democratic than it has been in this decade. In 1971, the world only had 31 democracies. Half of Europe was behind the Iron Curtain. Even in Western Europe, Spain and Portugal were fascist dictatorships. Greece was under the control of a military junta. Most of Latin America was under the control of military governments. Taiwan, South Korea, all dictatorships. Today they have all become democratic, and from 31 countries in 1971, today 103 countries are democracies, comprising about 2/3 of the world's countries and 2/3 of the world's population. Within countries as well, the power of governments to brutalize their citizens has been gradually curtailed. Capital punishment, which used to be pretty much universal, has been abolished in country after country. If current trends continue, they probably won't, but if you were to extrapolate the line for abolitions of capital punishment will vanish from the face of the earth in about 10 years. In another development, in country after country, homosexuality has been decriminalized. It used to be a criminal offense in just about every country, and every year another couple of countries decriminalize homosexuality. Child labor. In England in the mid-19th century, the era immortalized by Dickens in Oliver Twist, for example, about 1/3 of the children were put to work in farms and factories. Thanks to the premium on education, mechanization of agriculture, and an increased valuation of the lives of children, that went down to pretty close to zero, a trajectory that is now being replicated in the world as a whole. In 1950, also about 30% of the world's children were put to work. Today, it is now 10% and continuing to fall. Kailash Satyarthi won the Nobel Peace Prize a couple of years ago for his efforts, hugely successful in bringing down the rates of child labor. Violent crime. In the homicide statistics in many parts of the world go back 800 years to the Middle Ages. And in the 14th century, the homicide rate in England and Netherlands and other European countries was in the order of about 35 per 100,000 per year. Thanks to the frontier regions being brought under the control of the rule of law and the anarchy and the code of vendetta being replaced by a criminal justice system, that rate has fallen to about 1 per 100,000 per year, a 35-fold reduction. That is a process that seems to be replicated whenever frontier regions are brought under the rule of law. The same thing happened in New England when the anarchy of the frontier fell under the rule of law. Same thing happened in the American Wild West, made famous by the cowboy movies. And even parts of the world that today remain notorious for their high rates of violence, like Mexico, have had a 5-fold reduction compared to the rate of violence in the 1930s. That process has continued in the United States, which in rates of violence, as within many other areas of human flourishing, the United States is kind of a backwater when it comes to wealthy democracies. In pretty much every measure of human flourishing, we fall behind our democratic peers. Most notably homicide, where our rates of homicide have been between 5 and 10 times that of European countries. But even in the United States, the rate of homicide has fallen by more than half in just the last 25 years. It's not just the most extreme crime, namely homicide, that has shown reductions, but the rate of rape in the United States has fallen 75% since the 1970s. The rate of domestic violence has plummeted, and the victimization of children in schoolyards, in the home, rates of bullying, rates of physical abuse, rates of sexual abuse have all gone down. Indeed, we have become safer in just about every other way that you can imagine. Thanks to advances in the design of automobiles and highways, better licensing requirements, better traffic law enforcement, we are 96% less likely to die in a car crash compared to the early 20th century. We're 88% less likely to be mowed down on the sidewalk, 99% less likely to die in a plane crash, 59% less likely to fall to our deaths, 92% less likely to be burned to death, 90% less likely to drown, 92% less likely to be asphyxiated. There's one exception to this trend. And if I were to be able to show you the graph, you'd see a bunch of curves all going down for various accidental causes of death, but one of them going up. And that is the category that public health experts call death by poison, solid or liquid. At first, when I saw that curve, I wondered why people were suddenly drinking bleach or eating rat poison, but it turns out that that is the category that includes drug overdoses, and the opioid epidemic is one category of safety that has gone dramatically in the wrong direction. However, we're 95% less likely to be killed on the job, and we're globally far less likely to be killed in an act of God, in a earthquake, a brush fire, a volcano, a flood, a famine. What about the quintessential act of God? Everyone's favorite metaphor for an unpredictable date with death, the literal bolt from the blue, the thunderbolt hurled by Zeus. Yes, we are 96% less likely to die from a lightning strike compared to several decades ago. Knowledge. Through most of European history, no more than 15% of the population knew how to read or write. Today, that figure is 100% in the developed world, but in the world as a whole, the literacy rate has exceeded 80%, and for people under the age of 25, 90%. This is true not just for boys, as was traditional, but for girls. The world is approaching gender parity in literacy and in basic education. And in perhaps the most incredible example of human progress that I have come across, one that still strains most people's credulity, we are getting smarter. In a well-replicated effect called the Flynn effect, IQ scores have been increasing by 3 points a decade for almost a century, thanks mostly to the spread of education, probably also because of the rise of public health, and probably also the spread of symbols and abstract concepts into everyday life, trickling down from science, academia, and technology. Well, does any of this bring any gains in quality of life? All these things that economists like to measure and quantify? Well, by pretty much any definition of quality of life, yes. For example, as Charles Dickens reminded us in A Christmas Carol, in the 19th century, people worked about 65 hours a week. That has fallen by 22 hours a week. Most workers today get 3 weeks of paid vacation in addition to the reduced work week. In the domestic sphere, we used to spend about 60 hours a week on housework, and by we, that really means women, since housework traditionally and to a large extent today is gendered. But thanks to the ubiquity of electricity, running water, and labor-saving devices like refrigerators, vacuum cleaners, washing machines, dishwashers, and stoves, which a majority of households have, including a majority of poor households, the amount of time that we lose to housework has fallen from about 60 hours a week to about 15 hours a week. And in fact, an entire day of a week of one's life used to be called wash day. A day in which women did nothing but wash clothes, has been returned to our lives. Thanks to the reduction in the work week and the reduction in housework, leisure time has been increasing even since the 1960s, putting aside the gains from the early 20th century. If you were to see the graph, you'd see one anomaly, which is that the amount of leisure time for men has steadily increased. The amount of leisure time for women increased through the early 90s and then kind of leveled off. And the reason is that women spend more time today with their children. In fact, a single working mother today spends more hours a week with her children than a married stay-at-home mom spent in the 1950s. So forget Leave It to Beaver. We also spend less of our paycheck on necessities. In 1920, people had to fork over more than 60% of their paycheck to food, clothing, and shelter. Today, it's less than a third. Well, does any of this make any difference for our happiness? And the answer is, it does. In a majority of countries for which we have longitudinal data that tracks happiness over time, there's been an increase. The United States, by the way, is an exception. The United States, happiness has pretty much stagnated, although it hasn't gotten worse. And more generally, if we step back and we look at the effects of economic development on happiness, if we look at the full range of the scale from poor countries to rich countries, then we see that there is a very strong but logarithmic relationship between GDP per capita and happiness, both across countries and within countries. So as the world gets richer, its people on average get happier. Well, has this all happened at the expense of the environment? Initially, it surely did, but in a development that few people appreciate, the environment is rebounding. And in a kind of report card for the state of the environment that done at Yale University, the Environmental Progress Index, 78 out of 80 countries have shown an increase in environmental quality in the last several decades. This includes the United States, where since the passage of the Environmental Protection Act in 1970, our GDP has gone up. The number of miles that we drive every year has gone up. Our population has gone up, but the rate of emission of air pollutions at the same time has gone down. So the idea that's popular both among the hard green left and the hard libertarian right, that you can have environmental growth or you can have you can have economic growth or environmental protection, but you can't have both, is false. We have had both, thanks to environmental regulation, which, needless to say, are currently under threat. In temperate parts of the world, deforestation has basically fallen to zero as farms have been abandoned and are reclaimed by forest. Even in tropical forests, where there's still an alarming amount of deforestation, the amount of deforestation has peaked and has come way down. We have to bring that to zero, but the direction is downward. As the world has shipped more and more oil by sea, there have been fewer and fewer oil spills, and more of the Earth's surface, both land surface and oceans, are now protected against economic exploitation. About 15% of the world's land area and about 12% of the world's oceans. Well, I've reviewed case after case of what one would have to call human progress. How is this reflected in the news? Well, one more graph that, again, I'm going to have to pantomime because I can't project it. A data scientist used the technique of sentiment mapping, which automatically analyzes news stories for a degree of positivity, positive words and negative words. And what it has shown is that the New York Times has gotten pretty much more and more morose over time. That's not just the New York Times. A sample of the world's news sources shows the same increasing gloominess. So why do people deny progress? One answer comes from an interaction between the nature of human cognition and the nature of journalism. Amos Tversky and Daniel Kahneman identified a shortcut that the human brain takes, a rule of thumb by which we assess probability and risk and danger, called the availability heuristic. Namely, the easier it is to recall examples from memory, images, anecdotes, narratives, the more likely we think something is. Well, now think about how the news works. News is about stuff that happens. It's not about stuff that doesn't happen. You never see a reporter saying, here I am reporting live from a city that has not been struck by terrorists today, or a school that has not been shot up, or a country that has been at peace for 40 years. As long as the number of bad events hasn't fallen to zero, there will always be incidents to report on the news. You combine that with the availability heuristic, and you get the impression that the world is getting more dangerous and always has been. There are other psychological quirks that I think inflate our sense of dread and doom. In a phenomenon sometimes called the negativity bias, that bad is stronger than good. We dread losses more than we savor gains. We worry more about threats than we appreciate improvements. Lead to not only a sense that the world is always a dangerous place, but it kind of opens up a niche for professional curmudgeons and doomsayers and prophets to remind us of threats that we may have overlooked. Indeed, this sets up a kind of perverse prophecy market where the gloomiest, most morose prophets are the ones to which we accord the greatest moral seriousness. As Morgan Housel, the financial writer, put it, pessimists sound like they're trying to help you, optimists sound like they're trying to sell you something. Okay, let me conclude with three general questions about progress and enlightenment. One might reasonably ask, isn't it good to be pessimistic? Isn't it important to rake the muck, flick the comfortable, speak truth to power? Well, it is up to a point, but really what's important is to be accurate. That is, to be aware of problems and suffering and injustice where they occur, but also to be aware of ways in which they can be reduced. Because there are dangers to thoughtless pessimism. One of them is fatalism. Why waste time and money on a hopeless cause? Why throw money down a rat hole trying to alleviate poverty in the developing world if the poor will always be with you? It's precisely the conviction that we can improve, solve problems that gives us the confidence to solve the problems that remain. Also, thoughtless pessimism can give rise to radicalism, that if every institution is failing, if all our problems are intractable, if society is just spiraling downward, circling the drain, then we may as well raise the institutions of modernity, smash the machine, drain the swamp, burn the empire to the ground, empower a leader who promises only I can fix it, and out of the hope that anything would be better than what we have now. Well, that can be, as history reminds us, that can be a dangerous kind of desperation, because the sentiment that things can't get any worse can be wrong, is wrong, given how much better things have become, even with the problems that remain. Second question, is progress inevitable? And the answer is, of course not. There is no magical arc bending toward justice or tide of rising human improvement that will make things better off all by themselves. Quite the contrary, the laws of the universe are indifferent to human well-being, and left to their own devices, things get worse, not better. Solutions create new problems which have to be solved in their turn, and we can always be blindsided by nasty surprises, and they do happen, like the world wars, the 1960s crime boom, the opioid epidemic in the United States. Also, there are severe global challenges that we have not yet solved. Prominent among them are climate change and the threat of nuclear war, an improbable but potentially catastrophic event. I think we are best off seeing these as problems that are unsolved but solvable. Climate change must be addressed by decarbonization via carbon pricing, including carbon taxes, and low, zero, and eventually negative carbon technologies. Denuclearization ought to be pursued via enhancing international stability and programs of threat reduction and arms reduction. The two more graphs, which I would show you if I was showing graphs, show that progress in both of these endeavors is by no means a utopian aspiration, but to some extent it's been happening. If you plot the amount of CO2 that countries emit per dollar of GDP, you find that there is an arc that Britain, for example, first country to industrialize, had huge carbon emissions when it relied on wood and then coal, but then less as it switched to oil and gas and renewables and nuclear. The United States followed the same U-shaped curve. China has repeated that trajectory, India, and the world as a whole. So industrialization is not inexorably committed to flaming carbon, but decarbonization is a process that has begun. It has to be accelerated much more. It has to be brought to zero. But those graphs suggest that it is not impossible. Likewise, few people are aware that the world's nuclear arsenal has been reduced by 85% since the height of the Cold War. Indeed, about 10% of American energy comes from nuclear power from decommissioned Soviet weapons. Again, that ideally should be brought to zero. Final question that I'll raise. Does the Enlightenment somehow go against human nature? This is a frequent accusation from defenders of religion and nationalism, that humanism all sounds very good, but isn't it kind of arid or tepid or a flattened view of human life? As if the conquest of disease, famine, poverty, violence, and ignorance is boring. Do people need to believe in magic, a father in the sky, a strong chief to protect the tribe, myths of heroic ancestors? Well, I don't think so. For one thing, secular liberal democracies have proven themselves to be the happiest and healthiest places on Earth, probably in the history of our species, and they're the top destination of the people who vote with their feet. Also, I dare say that applying knowledge and sympathy to enhance human flourishing, when properly appreciated, is heroic, glorious, and, I dare say, spiritual.
I think that I cope with that question with a strategy of denial and repression now very effectively. I don't know what it would be like if the universe didn't exist, why there is a universe rather than no universe. But there's a grown-up version of that question, which is why is it this universe rather than some other universe? Why are the laws of physics like they are, like that we observe them around us, rather than some other way? And that is something, again, we don't know the answers. It's too big a question for us to answer right now, but we can imagine someday knowing the answers to that question. And people have ideas. Some people say, once we figure out what the laws of physics are, we'll realize that there simply is no other way that they could have been, that they're absolutely unique, there's only one way that physics can work consistently. And I suspect that that's not right, because I can imagine different laws of physics that seem to work fine to me. And in fact, when I imagine different laws of physics, I don't actually get the laws that are true in our universe. They're too complicated for me. So I think that we have different choices for what the laws of physics could be, and we seem to be stuck with some particular ones. Is that because there's lots of different universes, and we happen to live in this one? Is it because there's something that is better about these laws of physics than something else? Is it just because we got lucky, just some random number generator, and we won the lottery, and here we are with the various laws of physics that we have? So that is the closest question right now to what really keeps me up at night.
So why? It's the why
these particular laws of nature rather than some other laws?
Fascinating. Now, Catherine, is this something that bothers you, or you sleep fine through this one?
Well, I've always been an insomniac.
Oh, there you go.
But
so you had to go into physics.
But at the moment, I'm incredibly excited because the problem that I've been working on for 20 years is on the verge of being solved. What is the universe made of? So let me tell you what the problem is, and then I'll tell you about the action that's happening in this area right now. Most people consider that ordinary things, the chairs you're sitting on, the air you're breathing, the walls in the room, mountains, planets, that these things are the predominant constituents of the universe. These things are made of ordinary atoms, neutrons, protons, electrons. But the amazing fact is that all of this stuff put together only amounts to 4% of the universe. 4%. What's the other 96%? Well, dark matter is a quarter of it, and this is the problem that I've been working on. In fact, galaxies are made of dark matter. If you think about the Milky Way, The part that you see, the part you're familiar with, is a thin disk that houses the solar system, the planets, the stars, and so forth. And when you look out at the night sky, it's this thin disk that you're seeing. However, this thing is actually enveloped in an enormous spherical globe of dark matter. And that's the question, what is that dark matter? So most of the galaxy is made of something that we're really not familiar with, we're not comfortable with on a daily basis. 20 years ago, when I got into this game, there were two competing camps. There were the people who believed in machos and people who believed in wimps. So the machos are the massive, compact halo objects, M-A-C-H-O. These would be stars or stellar remnants and things like that. And on the other side, there are the WIMPs, the weakly interacting massive particles, W-I-M-P. And our work showed that machos are not going to cut it, so we concluded machos are dead, desperately looking for WIMPs. So these are particles that weigh about 100 times as much as the proton, but they're very hard to catch because they interact very weakly. So what people have to do is build sophisticated detectors that you either put underground or in space. And these are very difficult experiments where a WIMP comes along, hits your detector, deposits a little bit of energy. Somehow you have to capture this energy. So the exciting development in this, it's been going on for a couple decades, is that there were hints originally of anomalous events that people were thinking, maybe this is the dark matter. But there's been more and more of these, and there's a paper coming out in the next day or two, that means either Friday or Monday, I guess, that claims that there's a satellite called the Fermi satellite, which is really showing very strong evidence that maybe we really know what we're doing here and maybe these WIMPs have been discovered. So what keeps me up is the thought, wow, is this for real? I want to know what these things are in detail, and then if this is right, we have a model of stars called dark stars powered by the dark matter, and then I want to know if that's right. So I'm pretty excited.
So, Katie, does this mean that in the battle between machos and WIMPs, the WIMPs have inherited the universe?
The WIMPs have won.
That's good news for us WIMPs. What about you, Leo? What keeps you awake at night?
Well, I love what I do, and so mostly I sleep like a baby. However, sometimes I have administrative responsibilities, like running a group of people that do materials research or being in charge of the American Physical Society. And then I worry about how we physicists can most effectively and benignly contribute to the society around us. However, as a physicist, as a working physicist doing what I like to do, I have been connected with a set of problems that have to do with how complexity develops in the universe. You all saw on the run-up to this program beautiful pictures of the universe with the galaxies and the stars and the clouds of gases that form the universe. This is amazingly complicated, with different stars being different and different galaxies being different. This complication is something which arises from the very simple laws of physics, just the laws working themselves out in the natural way that they do. I don't actually work on galaxies and stars. I actually work on the flow of fluids and think about how waves and storms are produced by the flow of heat through the Earth's atmosphere, and think about how that complexity is analogous, perhaps, to the complexities that arise in other parts of life. For example, the complexities that have bedeviled us in the financial markets, or the complexities that interest us in thinking about how living things came to be formed and how the complexities of you and me and everybody in the world came about. I use the behavior of physical things as analogies to try to understand how other things develop their complexity. And it's fun, 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 and nothing to keep one up at night. It's to go to bed and feel that you have, in a tiny way, contributed to maybe understanding things a little bit better.
You know, Leo, Einstein used to say that the one thing he couldn't understand was the tax code, and that's fairly complex. So tell me, complexity, this is a really emerging area of science, isn't it? Trying to understand how small things, and you talk about fluids, but some of the rules that apply to fluids actually apply to galaxies, don't they?
Well, the thing which I found most exciting in much of my professional life was how laws apply on different scales of distance. The same law that applies on the scale of an apple applies on the scale of a moon. That was Newton's major contribution to our understanding of the universe. And that was a wonderful thing. And that's part of what physics does now, not with apples and moons, but other actors of a different kind. But the scale invariance of the universe is a wonderful thing to be studying.
Okay. What about you, Lawrence?
Well, I was told it was a family program, so I'm not really allowed to say what keeps me up at night. But I want to take a different tack, and because I am worried about some things. We have been incredibly successful, unheralded in a way. People don't realize the tremendous developments that have occurred in the last 30 years in our understanding of the fundamental structure of matter, the forces that govern matter, and also in our understanding, or at least our understanding of the way the universe is behaving. It's changed dramatically. And we've made such progress that I worry that we are, in some sense, almost an embarrassment of riches. I worry whether we've come to the limits of empirical science when it comes to our understanding of the very small and the very large. We have this cockamamie picture of the universe, which is even more cockamamie than Katie talked about. Dark matter is almost sane. 70% of the universe is empty space. The energy of empty space dominates the energy of the universe. We don't understand why it's there. An incredible mystery. But it could be that our discoveries have taken us to the point that we may not be able to empirically answer the questions we're asking, almost along the lines of what Sean was saying. Namely, we have one universe, and that may just not be enough to answer the questions. We may need more than one universe to know the answer. Because, of course, if there are more than one universe, then in fact, we may be an outlier, and so things we measure might be statistically rare. And we may just simply not have access to the empirical data that allows us to fundamentally determine the answers to those questions. Similarly, on the very small scales, we're very excited that the Large Hadron Collider is about to turn on, create a black hole, and destroy the universe. But before it does that,
Physicists said that.
We're very excited that this machine is going to turn on, and it may address fundamental questions that have been bothering particle physicists, unanswered questions for 30, 40 years. But it may not answer those questions, and it may be, again, that in order to answer them, we may have to rely on theory and not experiment. And now, that is a scary prospect. It won't mean that science ends, I think. It'll just mean the nature of science may change. But losing that empirical handle may be dramatic. And then at the same time, at the other end, what really worries me is that we've lost the empirical handle in our daily lives, that somehow the internet and 24-hour news channels, which are supposed to have been increasing information, have done just the opposite. When I'm in my country, when I can hear that Stephen Hawking, had he lived in England, would be dead because he would have had to rely on the British healthcare system, when in fact, of course, he does live in England, has always relied on the British healthcare system. But when I can hear that kind of nonsense pervade on television and in columns, I really worry that we've lost our empirical handle on reality. And as someone who's vitally interested in science and social issues, that keeps me up more than perhaps the first question.
By empirical, you mean being able to falsify it, being able to test for it, rather than just have theories that you can't test?
Well, not only theories that you can't test, but you hit the word falsify. It's a word we don't use very often, because the biggest misconception about science is that it tells us what's true. It doesn't do that at all. It tells us what's false. And by knowing what's false, it's like Sherlock Holmes. You get rid of what's false and you hope what's left is closer to the truth. But you never know that any theory is absolutely true. And the only way to find out to make progress is to be able to rule things out. So falsifiability is very important.
That's the biggest, by the way, get-out clause I've ever heard. So you say you can't really understand the universe unless you get some other universes. Right? So you're basically saying, if you get it wrong, well, I can't blame me. I haven't got other universes.
Exactly. That's right.
Very smart, Lawrence. I can see what you're doing well. What about you, Gino?
Well, I wonder how to get to another universe. And I'll have to check with my friends here later on some tourist information. But, and maybe the Ministry of Tourism would be interested in that, you know.
You heard it here first in Waterloo.
Possibilities. We are a little kooky here at times. Well, I was thinking, one of the things that interests me, when I heard in Neil's introduction, he evoked some of the greats of the past, and in particular he talked about Newton, Einstein, Heisenberg, Dirac, and people like that. And one thing I realized in listening to him, that Newton was 25 when the apple fell on his head, proverbially, namely when he first realized the theory of gravitation and developed calculus. Einstein was 25 when he thought of the theory of relativity. Dirac was 25 when he thought of his great relativistic equation. Heisenberg was 23 when he thought about quantum mechanics. So here we have a group of wise men and women. But, you know, I really think it's going to be these 23-year-old, 24-year-old, 25-year-olds who are going to come along and one day say to us, you're all wrong. Your ideas are all, this is the way it is. And I would really like to, this is in part a plea to those of you in the audience who are 23 or 20, and to those of you who are perhaps viewing or listening. Think crazy ideas, think wild ideas. We don't have the answers. Of course, you know, this may be the end of science, but it may be the beginning of something that is so exciting that we have no idea what it is. And I lie awake at night thinking, what is the craziest thing I can think of? And then I fall asleep.
So tell me, Gina, you're saying basically you're washed up.
Not only is this kooky, but this panel is cruel.
Okay, David, what keeps you awake at night?
Well, I'm going to tell you about something that used to keep me awake at night, but which I finally reconciled myself to, so I sleep very soundly. I spent a lot of my time working on string theory. So for those of you who don't know what this is, it's supposed to be, it's certainly advertised as this super-duper theory of everything that's going to explain all the problems in physics. It's going to reconcile quantum, it's going to reconcile gravity that Einstein gave us with quantum mechanics, the very big and the very small. And it's supposed to be the most beautiful theory ever written down. I actually think it is an extremely beautiful theory. But the thing that kept me awake at night was wanting to know how we're ever going to know if this theory is correct. Or more specifically, how I'm ever going to know if this theory is correct within my lifetime, which is all I really cared about. And this sort of comes back to Lawrence's point. You know, the experimental timescale for particle physics is about 30 years. You know, the LHC is going to turn on next month. This is the new particle collider in Geneva, in CERN. And we very much hope it's going to discover fantastic new things, but it seems very unlikely it's going to give us any hints that string theory is the correct theory. It may discover extra dimensions of the universe or something spectacular, but you know, it's kind of a long shot. Or there's other experiments that we can do. We've sent up satellites that measure the afterglow of the Big Bang. It's called the cosmic microwave background radiation. And we study the patterns in these afterglows, and this tells us what happened during the first few fractions of a second after the Big Bang. And if you're lucky, maybe string theory was at work there and was creating an imprint which we can detect. But again, you've got to be kind of lucky, and it's just not clear that we're ever going to know whether string theory is right, or as Lawrence said, the key point as to whether it's wrong, which would be the best thing to do, just rule it out. So this used to keep me awake at night. I was spending all this time working on a theory that I certainly thought had a possibility to be right, but probably would never know within my lifetime. So that did keep me awake. What happened that allowed me to sleep was something quite remarkable. It came as quite a surprise to all string theorists. It turns out that the equations that we use in string theory are actually useful. meaning useful to apply to other physical systems which we do experiments on and which we can test. So even though string theory may or may not be right, or probably we'll just never know, it is a useful theory. And so these days I spend half my time thinking about whether string theory could be the theory of everything, and the other half of my time just trying to make it work to understand other aspects of the world, things to do with quarks or to do with the way strange metals work, down-to-earth things. And so sort of balancing my time this way, I sleep pretty well now.
So David, you're saying that it's another get-out clause. You're saying if it doesn't explain the universe, at least it could explain how long the rinse cycle is going to be on my washing machine. Is that right?
Yeah, it's pretty good for that, actually, yeah.
There you go. Neil, what keeps you awake at night?
Well, it's certainly not pessimism about the future. I've never really seen the point of pessimism. I mean, my philosophy is go for it, and if you fail, at least you tried. So I share none of Lawrence's or David's concerns on that front. I think we are absolutely blessed to be living at a time where science has made incredible discoveries. Who would have imagined? I mean, Katie and I were both in cosmology, I guess, in 1990. And we didn't imagine what was coming. We have mapped the whole universe. We've learned an incredible amount of information. A lot of our theoretical ideas have turned out to be correct about the basic laws governing the universe. So I find this note of pessimism really surprising, and it's maybe a sign of our culture that we seek instant gratification. I don't think we should. We're part of a long and wonderful tradition. And I think, frankly, if all we did was, like classical musicians do, represent these marvelous equations and laws discovered by earlier generations and perfect the presentation of them or our understanding, that itself would be a magnificent way to spend our time. But of course we want to do much more. And I think the two things which keep me awake at night are, first of all, wondering about the singularity of the Big Bang. Everything we see came out of the singularity. We don't know how to describe it. All of our equations fail there, all of these equations of string theory. Again, I don't really understand why string theorists ever believed they had a theory of everything unless they had described the beginning, the singularity itself. So that's what I work on. I think the tools emerging from string theory, which, as David has explained, is a beautiful mathematical structure. These tools give us new ways to think about this problem, and ways which are deeply satisfying in a mathematical sense, whereas the conventional description based on Einstein's theory just falls apart. So I think that's very exciting. The other thing that keeps me awake at night is worrying about how we are going to take advantage of the new opportunities in the world, meaning communication, instant information, the web, growing sense that the world is one community. How are we going to take advantage of this to reorganize the way we do physics? Traditionally, certainly theoretical physics has been viewed as a more or less accidental subject. I mean, Einstein was in a patent office, a completely unknown person who made the most sensational breakthroughs. Newton, again, worked alone. We know this is changing. The world doesn't work that way anymore. Can we invest strategically in our society to speed up the rate of discovery and understanding? And this is critically important for our future, that we do that, because we need new breakthroughs, and most of all in physics, to deal with all the crises facing the world and the challenges, getting off the planet into space, dealing with energy, global warming, better communication. And so I think we have to actually change the way we do physics to take advantage of all the modern opportunities. So I'm a total optimist, and I say, forget the pessimists.
Neil, you have you were talking about two examples, Newton and Einstein, who both came out of places that you'd be surprised. But in both cases, it's interesting that they had time to think. Newton, in the case of because of the Black Plague, had shut down the universities, so he had a lot of time on his hands. Einstein has a different problem. He was just bored out of his mind. So you're recommending that we just bore people out of their minds and they'll find something? Or that we shut down universities and actually...
Actually, Einstein was not bored at all. He was absolutely driven. And if you see the recent film about his life, you'll see what happened. And he was rushing back and forth between Switzerland and Germany and frantically developing his theory.
He wasn't obsessed with patents, though.
What?
He wasn't obsessed with patents.
Oh, no, patents was irrelevant. And I think we have the same, the young people who work here, for example, are equally driven. They want to know the answer. They are unafraid of the fact that it's really hard to make progress at that level, and they want to try. And so I think long may that continue. And if it takes us another 50 years or 100 years for the next breakthrough like Einstein made, it will be well worth it. And we have to prepare for that.
David, that's not your horizon at 50 years. It's not the horizon you're talking about, though. Andrew, what is it that keeps you awake at night?
Well, like Lawrence, I was warned that this was a family show, so I can tell you quite honestly that for the last 18 months, what's kept waking me at night has been wet nappies. Not mine, our son's. But after I put him back to bed, I get to sit up for an hour or two and think about physics without interruptions, which is a guilty pleasure. And the thing that I've been thinking about a lot is an old question for physicists, actually, one that Schrödinger asked in the 40s, which is, what is life? And in particular, given the fact that we're currently living through a second quantum revolution, what, if any, are the implications of that for life? So I should explain that about 100 years ago, the first quantum revolution was the realization that the smallest components of matter and the smallest components of light behave by these odd rules, which we call quantum mechanics. The second quantum revolution, which has really only started in the last 10 years, is the realization that they can be correlated in ways that has been known about since the 1930s. It's called entanglement. And they're funny correlations. If you did it in a card game, you get shot. Einstein didn't like it. He called it spooky action at a distance. And for about 70 years, physicists went, oh, they're weird. But for about the last 15 or 20, we've realized we can exploit them. We can do quantum computing, which Neil mentioned in his opening address. We can make powerful measuring devices and do things that are just currently impossible without using entanglement. And in the last couple of years, there's been hints that, in fact, in biological systems, which are wet, warm, messy things, they might be exploiting entanglement, which I find fascinating. So there's people doing measurements on that, not me. I try and build a quantum computer as my day job when I'm not sitting up at night. But we are trying to model that up with these quantum systems, and perhaps life has something to teach us as well. If I look at chemistry as an example, there are a lot of processes where we need high temperatures and high pressures and poisonous chemicals to make a product, and something wet does it at room temperature quite nicely. And the other thing that comes into that, if every time we find something in physics, not every time, nearly every time we find a new phenomena in physics, we find out that biology got there ahead of us. So sonar, electricity, electric eels. The platypus from my country has a bill that can detect a 9-volt battery dropped in the other end of a 10-foot tank. So really weird properties. We found a shrimp last year that can measure all the polarization information of light, which humanity only discovered in 1852, but it's been doing it for several million years. So that's what I've been thinking about at night.
Wow, fascinating. I had no idea. So entanglement is that idea where you do something with atoms in one place and a seemingly unconnected group of atoms do something else. Is that right? Or is that a journalist getting it right?
Okay. What entanglement really is if you and I have a pair of entangled particles and you do measurements on it, you'll get noise. It'll look like random numbers. And I'll get noise and it'll look like random numbers. But when we get together in the pub afterwards, we'll find no matter what measurements we made, we got correlated random numbers. So you can't send information faster than the speed of light, but somehow there's some influence that's there even though we weren't talking to one another.
So we've got the same random numbers.
The same random numbers.
Wow, cool. That's a cool trick. Anton, you've got the mic. You don't need to.
I don't know if this one works.
You call that a mic?
There's a Crocodile Dundee reference, by the way. Anton, what keeps you awake at night?
Well, basically that's a tough question because I have a very good sleep and I usually have no problems first not
They're all
falling
great
asleep.
sleepers, aren't they?
But if there were something which would keep me from falling asleep, then it's a very broad question. It's the question, how far are we along the road? I mean, we do science only, if you just lean back a little bit, the scientific enterprise is less than half a millennium, which is nothing in the history of mankind. It's really nothing. I mean, about 400 years ago, Galileo discovered that you can do experiments, that you can be so arrogant to ask nature what nature would do. You know, this was unthinkable for people before. Or people like Kepler discovered the idea that you can have quantitative laws of nature, which is also something unheard of before. So there are people who think that we are just close to having a theory for everything around the corner. When somebody says that, and I don't want to be derogative here, when somebody says that, in my eyes, I hope that he just exposes the limits of his fantasy. That the things are, that we are very far from understanding. I mean, my personal feeling is that we have started to scratch the surface. The whole enterprise will go on for very long. The question is how fast it will go on. And that really then might keep me awake, because how much of this will I be seeing in my life? Because I want to see the new breakthroughs. I want to see what will be going on. And there are hints of, possible hints of where things are really interesting. You heard some of those here. Another one is the question, what do we really describe in physics? Do we describe reality? Is it out there? This was the basic tenet in science, in physics, and the biologists still believe that. But in physics, you heard the notion entanglement. I might give you a simple example so you understand immediately what entanglement is. If you had a pair of dice which are quantum entangled, you can't buy them yet, but I'm sure in 100 years you can buy them as a Christmas present. So the pair of quantum dice would be such that if you throw one die here and another one over there, they always show the same number. Now, this can only be if they have a common cause or if they are talking to each other somehow. Now, we have ruled out in experiments either of these explanations. So we have something which is completely random, and in quantum mechanics believe that this is a new kind of randomness where there is no hidden cause. There's nothing telling the die what to do, but the two dice do the same, separated over a large distance. Now, how can we make sense out of that? Now, what this tells us also in a deeper way is there are situations where what we observe in experiment is not some reality which was there before. Our experiment creates reality in a sense. Now, what is then reality really? What are we describing in our physical theories? And I think these ideas may have the possibility to go beyond, to find new ways. I mean, quantum mechanics is 100 years old, relativity theory is 100 years old, a new breakthrough is due. The question is, where would it happen? And maybe it happens when we really start to understand what reality is and how it is related to knowledge and to our actions.
It sounds like from what everyone's saying that the answers come when things unexpected happen. You talked about dark matter and dark energy. You talked about entanglement. Things that you weren't expecting tell you there's something you don't understand, something's missing. Is that the general feel?
Well, that is sometimes the case, but it could also be a new viewpoint. It could be a unification of ideas which were different before. Newton was mentioned. Newton unified the laws on Earth with the laws in heaven. You know, he showed us that this is the same kind of law. Unification, unifying different concepts. And maybe we have to unify things to go beyond what we did so far. Maybe we have to unify the concept of reality and information. This is my personal feeling. So it is not necessarily that there is something which we don't explain yet. It could be a completely new viewpoint of things which you have had before, and then everybody would say, my God, why didn't I see that?
So it might be a case of a Rubik's Cube type of solution, that The data is there, but you can't see it.
Right.
You can't recognize it. That's interesting. Right. Do you think, Katie, that there's dark energy and dark matter offer an insight, perhaps, into this? Because it is pretty mysterious, isn't it?
I think you have a point. The whole picture we have of dark matter and dark energy, the idea that the universe has 4% atoms, 25% dark matter, and the rest dark energy, that is moving forward from a lot of assumptions about how things work that we have now. I think it's possible that somebody could come along and say, wait a minute, you guys, here's a theoretical perspective that you have missed before. And if you look at it in a completely new way, then you'll get a new answer. So in the same way that Newton's laws, they're beautiful, they're right, but they're limited. Einstein had to come along and correct them. The same thing could happen again. We're using Einstein's equations. Maybe we need to correct those. So as far as dark energy goes, some of us have been playing around with changing Einstein's equations, but not doing very well, frankly. So there may be something really seriously, theoretically wrong that we're doing. So I think both approaches are necessary. New data, yes. The new theory, yes.
It's not may. There's certainly something we're doing wrong. I mean, we know that. That's why we do science, because we want to be... That's the other thing people don't understand about science. They think it's some secret pact that we have to make sure that we don't want to allow any other ideas in. In fact, what you want to do is go into work every day and show that your colleagues are wrong, right? Because that's how you make an impact. And so the idea, we know that there's things we're doing that are wrong. If we had all the answers, it wouldn't be any fun.
This is actually a profession where people enjoy taking each other apart. Have you guys ever thought about worldwide wrestling? It's kind of an example of physics, you know. Is there any hope there, David? I think it sounds like, because I'm focused on your plight, that you really want something resolved, string theory for real or not. You want to be able to falsify. Is there any hope, do you think?
There's certainly hope. So I mentioned the LHC is turning on.
That's the Large Hadron Collider.
That's the Large Hadron Collider, the new particle accelerator. It turned on last year, it got broke, it got fixed, and it turns on again next month.
Because somebody pulled out the plug or forgot something.
Yeah, there's a little helium leak. It was a bit of a mistake.
Dropped their lunch.
So this will make some discoveries that we expect to see. You'll hopefully find the Higgs boson. I think most physicists believe that this is going to happen. And then there's a whole slew of possibilities for what it could find afterwards. And a whole slew of theoretical models where people will be jumping up and down hoping that the experiment matches their theory. And some of these things that we see could be shouting at us that, oh, it's string theory, there's extra dimensions in the universe, lots of exciting things. I think that, as you mentioned, what we really hope for is just a surprise. It's something which is distinctive, but doesn't fit into any of the categories of things that we expect, and is really going to force us to rethink our ideas about what's happening at these very small distance scales.
So, for example, would be something like one of the things that Large Hadron Collider was theoretically built for is to find a theoretical particle called a Higgs boson. Would you say that then? I'm open this to the panel. Would you say that not finding the Higgs boson would actually be the best result?
Well, then everything we know is wrong. So in that sense, yes.
It would be the best result except for sociologically.
You'd be depressed.
No, I mean, it would be unlikely that we'd get to build a new accelerator which would tell us the answers. And
They'd never trust you again.
But I think it is scientifically that many people don't realize that null results are sometimes, I mean, in the case of Einstein, in fact, at the university I used to teach at, Michelson-Morley experiment didn't get what we thought was the right answer, and they got a null result, and it dramatically affected things. So yeah, nothing would be very exciting, except it would be very difficult to get Congress to spend more money.
We ought to recognize, am I on? Yeah. Yep. We ought to recognize, however, that physics is broader than the discussion we have had up to now. The majority of physicists do not work on cosmology, nor do they work on particle physics, the two major subjects of the discussion up to now. Just as we do not know very well how the universe began, we also do not know and understand very well how ordinary window glass works and keeps its shape. Just as we do not understand the interactions of the most fundamental particles in the universe, We do not understand how magnetic fields are generated within the Earth and within the solar system. These other problems are the bread and butter of many of the physicists who work in the world. As the fundamental problems attract our attention, we should also recognize that the universe around us, chairs and the tables and the magnetic fields and the gases around us, are interesting and only partially understood. We will understand ourselves and our world better as we understand window glass and magnetic fields. And the investigation of these more familiar things are as important to physics as the investigations of cosmology and particle physics. They furthermore have the advantage that we might hope that in some cases they will have a shorter time frame for their understanding, that a graduate student who starts now might, by the time he or she gets his or her PhD, understand a little better how glasses work and understand a little better the magnetic fields in the universe.
That's a valid point, because superconduction is probably a really good example. That would have a dramatic impact on our society. The resistance that you have from electricity, generating electricity in one place and delivering it somewhere else, if you could conduct that electricity with very little resistance, you actually could, you wouldn't have to build nuclear power stations or build any power stations anymore, would you? I mean, does anyone want to talk to that? Are there fundamental problems like that? Sean, please. He needs a mic.
Thanks.
Oh, it's very kind of you to hand it over, Lawrence.
Well, I think what I can do is point out that the problems that Leo very, very rightly says are extremely important and hard to figure out are, as was alluded to earlier, connected to these other problems of cosmology and quantum mechanics, and similar techniques are brought to bear on them. One of physicists' favorite concepts is entropy. And we talk about entropy as a measure of disorder. If a deck of cards is all in the right order, then it's low entropy, it's orderly, it's organized. If it's just shuffled randomly, then it's high entropy. And when we go to, and the concept of entropy was invented, why? Because people wanted to make better steam engines. In fact, the second law of thermodynamics was brought about because Saji Carnot was a French engineer and physicist, and he was upset that the English were making better steam engines than the French. He ended up inventing the second law of thermodynamics and leading to entropy, and this is a very down-to-earth concept that is operative everywhere in our everyday lives. It is also, in my mind, the single most important puzzle to modern cosmology. We start in a universe which is very, very low entropy, near the Big Bang, where all the puzzles are, as Neil mentioned, and entropy increases as time goes on. We have a medium-sized entropy today. It will be very, very high in the future. So that fact, that it starts low, gets higher, will be higher in the future, everyone agrees on. But here's another fact that is a little bit harder to understand. The early universe was simple. It's easy to describe the early universe. It was hot and dense and smooth. That's it. That's the entire description. The very, very late universe will be simple. It'll be empty space. Everything that we know, all of us, all the stars are going to collapse into black holes, and if you wait long enough, 1 Google years from now, all those black holes are going to evaporate, and there'll be nothing left in the universe but empty space.
That's like a lot of zeros rather than a search engine.
A Google is 10 to the 100, not the search engine. So, but in between, today, the universe is complex. All the stuff that Leo says we need to think about are manifested right in front of our faces. So entropy just goes up, but complexity starts low, goes up, and then goes down again. Why? Why is that the way it works? We don't know a good answer to that. And it's a kind of problem that connects cosmology to the underlying laws of physics, to the everyday complexity that we're still trying to make sense of when we try to understand window glass or coffee cups or computers or anything like that.
I want to ask
I want to just show the ecumenical nature of science by agreeing with Leo, and in fact, saying that he didn't stress it enough, that there's another aspect of physics that we haven't really stressed, and that's its utility, and that much of what physicists do actually makes people's lives better in one way or another. And in fact, the Nobel Prize this year A lot of people said, "Oh, gee, that's not very profound, optical fiber or CCDs," but it wasn't. But it's changed the world, and so physics has the stuff I do and the stuff many people in this panel do are never going to have any technological applications, never, ever, ever, and that's just life. But a lot of physics has profound impact on our lives, and the kind of physics that Leo's talking about can have profound impact in the short term as well as the long term.
Now, wait a minute, Lawrence. The kind of physics we do. Okay, so what's the biggest thing of a practical nature that came out of particle experiments, accelerators?
World Wide Web.
World Wide Web. So
Yeah,
that's the point. You fundamental
yeah,
science,
but
who knows? So there were these enormous data sets that people had to access all over the world. And a brilliant, Berners-Lee at CERN had this brilliant idea to create the World Wide Web, and you could access it from your university. So you never know.
Yeah, you never know, but I think it's the one thing I think is dangerous, and people in our field did this when the superconducting supercollider died. You shouldn't justify a field by its spin-offs. Particle physics and cosmology are interesting to do because they're exciting aspects of the human intellect, and understanding nature and our place in the universe is profound and important. And just like you don't have to ask what the utility of a Picasso painting is, you don't have to ask what the utility of maybe even string theory is, God forbid. But you're right, there are side benefits, but I really don't think we should justify our field. It's not unlikely that discovery of dark matter is going to have an impact, but that's not the reason it's worth understanding it.
Don't forget, we have matter, antimatter annihilation powering engines in Star Trek.
Yeah, I know, I wrote a book about it, yeah.
I know, that's why I said.
A little bit of time for this side of the...
Yes.
I just wanted to underline what Leo said about the usefulness of knowledge about glasses and magnetic fields and so on, but also to remember that a lot of the things that we know about how electrical conductivity and the properties of matter came from discovering quantum mechanics, and the problems that quantum mechanics set out to solve were not how magnetic fields work or how conductivity works, but were a different set of problems. But they developed some tools which then blossomed. And so I'm frankly encouraged to hear that string theorists are developing new tools that maybe will have some applications that we can't even think about, and that's good.
Anton.
So
Whoa! He was firing a laser beam at
the
you.
two should not point to each other. Yeah? I want to kind of extend on what Leo said about this, many other fields. Sometimes students come to me and say, or have afraid that what they are working on right now is boring. And I tell them, if this is boring to you, you have not looked close enough. Every problem in physics, at least, probably in science, is interesting when you look close at it. And when you look deep at it, when you ask deep questions, it's fascinating, and not just the origin of the universe and things like that. And about possible applications, when somebody asked me 20 years ago, when it happened, journalists asked me, what is it good for, what I'm doing? I was doing experiments in the foundations of quantum mechanics. I told them I can proudly answer this is not good for anything. It's as useful, I didn't mention Picasso, I said it's as useful as a Beethoven symphony. Quite arrogant, right? I mean, but I was younger. I'm from Vienna, okay. We do this because it's part of being human. It's part of being human to like to know what is behind the next hill, what are the next interesting questions. The same way as we like to do music, as we like to have art. Now, I was completely surprised by the fact that this kind of work now leads to new ideas for information technology, quantum computer and all this. This was a shock. This was a shock for many people in the field. And that's going to happen again and again. So I think we should not justify science by specific applications, because this is completely unpredictable. But they are going to happen anyway.
Yeah, the common example is, studying boring old molds led to penicillin and antibiotics. So, it's worth doing. Neil, I've got to pick up something that Sean said, and I think it seems to conflict with what you were saying. Sean said that the universe at the beginning was hot and smooth and basically simple, but you were saying that the singularity, which is the beginning of the universe, is actually extremely complex. What's it going to be, Neil?
The truth is that none of our current theories describe the singularity. We know it's there. It's staring us in the face. We look out into space. We are looking right at the singularity because the light we receive from far away was emitted a long time ago. And so we can see the singularity. In the future, we will measure gravitational waves. They haven't been detected yet, but they should be detected within the next 5 or 10 years.
You're confident of that?
Absolutely. This is almost a sure thing. We trust Einstein's theory enough to know that we also have observed very good evidence for black holes. We know these things collide, they will emit gravity waves, we'll detect them. When we do that, we'll open an entirely new window on the universe, and we'll be able to use those gravitational waves to look right back to the singularity itself. So that's a very exciting thing. It's long term. It won't tell us how to build better windows or better materials, but over the next 100, maybe 200 years, we will be actually making maps of the Big Bang singularity. And so the theories we develop now will be tested.
I'm going to follow on with another question, but before I do, if you have a question of your own that you'd like to ask the panel, please come to the microphone just here. It's okay, nobody will notice that you're there in the dark, you won't be seen. Please ask your question, identify yourself, and we'll do that in about 5 minutes. We'll come across to you. We're also going to be taking questions from people who are watching online. So if you have a question online, please submit it now. Neil, you're saying that, is it because at the very beginning of the universe things were so hot and smooth that actually the laws that we have don't quite work, or we don't quite understand what's happening?
No, it's much simpler than that. It's that the universe is expanding. And so if you trace time backwards, it's contracting. It was much smaller in the past. And if we trace it back 13.7 billion years ago, everything we now see was at the same point. The universe shrank to 0 size, the density went to infinity, and all the equations fall apart.
Right.
So that tells us there's something wrong with our description of the Big Bang. And that's where these new ideas come in that allow you to actually describe what happened at the singularity. And there are basically two very interesting options. One is that it was the beginning, and for that you need an entirely new approach to physics. You need to be able to explain how time can start. Nobody has any good idea about that.
Not even Lawrence.
Not even Lawrence. And the other possibility, which in my view is more conservative and simpler, is that the Big Bang was a violent event in time. But that means, that's even more amazing, that means there was a universe before the Big Bang.
So you're wondering what banged before the bang?
Yeah.
The bang. Leo, do you think he's wasting his time and should get on to doing something that's more useful?
How could we do anything more useful than discuss the nature of the intellectual activities that are sponsored by the people around us? I wanted, however, to comment on something that happened in the exchange up and back here in this room. I mentioned the familiar, that is window glass and magnetic fields, and my colleagues jumped on applications. Now, it is not, I work on condensed matter physics, that is familiar things, not because they have applications, but because they are deep and important to understand. I would like to express that depth to you by going on with the discussion of complexity, which I started with a moment ago. You all, me, everybody, are rather complex. We have had a discussion for many hundreds of years as to whether living beings like us are the results of a natural process or the results of a divine intervention. That is an important and useful and significant intellectual discussion. That discussion will be advanced if we understand better how complexity is produced in the universe. It will be the discussion of how many angels will dance on the head of a pin if we do not further understand complexity. So that, in fact, the richness of the universe is something which directly influences what we tell ourselves about ourselves and what we tell the children, our children, about the world. And physics directly influences our view of ourselves and our children through many of the subjects we have discussed here, including some of them which people jumped on as applications, and I would say are important and significant intellectual studies of the familiar.
I think, Leo, that was a response to, you know, when funding agencies come around, the first thing they say is, oh, yeah, we did with all these applications, though.
But I just want, it's the first time I'm ever going to disagree with you about something you said, Leo. Profoundly disagree with you. Just so people don't get the illusion that the discussion about whether humans are natural or divine is important. It's entirely unimportant, irrelevant, and a useless discussion that we should stop having.
So other than that, you agree with it?
I'd just like to point out that's a discussion that only seems to be still happening in North America. In the rest of the world, it's over.
South of the Canadian border. No, it's in Canada.
Perhaps between Mexico and Canada.
So we have a question.
Yes. This question is for the whole panel. Do you want me to introduce myself?
No, it's fine.
Okay. I'm Edgar Bering, a student at the University of Waterloo in mathematics, and you were talking about the new methods that string theory is producing. Now, Newton brought up the calculus, which is fundamentally a continuous process. It works on continuous things, and discontinuities make it break. And Einstein generalized that, but he still used differential geometry, which is just a more general continuous setting. Now, are the methods string theory coming up still continuous, or do you think you need discrete methods like Conway used when he proved the free will theorem with a very elegant combinatorial argument? Is this the end of continuous methods in physics, or can you keep going with that?
Can I just see if I understand this? Do we need a new mathematics, is that what you're saying?
Not a new mathematics. Take from a different branch, combinatorics, which works over discrete things and counting and enumeration arguments instead of continuous things.
Okay, that's interesting.
So the kind of mathematics you're describing has not really been that useful in string theory, and string theory hasn't really had a big impact on it. So the kind of mathematics that arises in string theory is the continuous type, the type that we've been using for hundreds of years. But it is worth saying that as well as string theory developing tools to understand basic physical systems, Leo was insisting that you know, we care about window glass. I completely agree with him. One of the things string theorists are doing at the moment is to try and understand the conductivity in high-temperature superconductors. So something that's profoundly interesting, but also potentially very useful. But on the other side of things, it's also given rise to new ideas in mathematics. So really revolutionized certain areas of mathematics. Indeed, Ed Witten, who's one of the leading string theorists, won the Fields Medal in mathematics. This is the equivalent of the Nobel Prize. So it is changing areas of mathematics, but not the particular areas that you mentioned.
Jennifer Dodd from Perimeter, you have a question that's come in on your BlackBerry.
I do. I'm bringing in a question from the online audience. Tatiana from Toronto asks, in the last few decades, which of the initially promising and popular theories in physics turned out to be incorrect, at least as far as we know today?
Is that one of yours, Lawrence?
Well, a lot of mine, actually, but most of them. But I don't know whether they were the most promising, but they were incorrect. But one of the things is, in fact, something that Katie brought up, and we thought the universe was made of matter. In fact, we were sure that dark matter, we were so proud of dark matter that we were sure that it was 99% of the mass of the universe, and then we discovered that we were wrong, that in fact empty space is far more dominant. And that was a shock to everybody. That's one example. I mean, it was something we were all working towards. We were pretty certain that it was right, and it was wrong.
Actually, another example was until 1998, it was thought that the universe, it was unknown whether it was going to continue to expand or it might actually contract back again. And then dark energy came along and kind of threw a spanner.
Well, we still don't know the ultimate future of the universe. The ultimate future of the universe is still up for grabs in spite of the fact that we know what's happening now. So that question still is there.
To take a more earthy example, 4 years before I was born, people thought the continents didn't move. which I find amazing because I grew up knowing that continents move around, and then I talk to people just slightly older than me, and they say, no, when we went to school, the continents stayed where they were.
Because they're made of rock.
Well, yeah.
Well, but that's the thing. Even a child looking at a map of the world realizes that things look like they fit into each other.
But there are many. People thought genes were made of proteins. People thought that the limit of superconductivity was 23 degrees Celsius or so above absolute, 23 degrees Celsius above absolute zero, and people thought genes are made of proteins. That's what makes science so much fun. You get to go and prove people are wrong, as Larry said.
Do you have another question, Jennifer?
Yes, I have a second one. Earl Howard from Toronto, Ontario wants to know if the corollary of the Big Bang Theory is that the universe is expanding, from where and to where is it expanding?
Well, I don't know. Well, you want to take
Who wants to take this one?
I'll see if
Well, I think that... Yeah. I think that's a good question, and it's exactly what we are working on and trying to develop new theoretical tools which will help us to understand, can a space-time, like the one we inhabit, emerge from nothing, or does it emerge from a violent event, which we call the singularity? And so that's exactly the questions we're discussing. And the future of the universe is of the same form. The discussion of the future is, will the universe simply continue to get more and more dispersed, empty, vacuous, and end in a whimper, a very long one that goes on forever? Or will there be another singularity in our future, perhaps a bang after that? So the way we explore these things is not through philosophy. We actually try to develop very concrete mathematical models and make them as consistent as we can, and then try to test them through observations.
But I think that there was a misconception, though, in that question that we should address. People often think the Big Bang happened in a place and then we're all moving away from that place. That's not true. In our picture, the Big Bang was everywhere. And it happened everywhere. There is no center of the universe. We're not necessarily expanding into anything. Space can expand without expanding into anything. And the Big Bang didn't happen in a place that we can point in our universe. Everywhere that we now see was part of the Big Bang. So that's a more basic thing.
Except, Lawrence, everywhere was a very small place.
Yeah. Yeah.
I've been everywhere, man, kind of thing. Would have been very easy at the beginning of the universe. Sir, you have a question. Please come up to the mic and identify yourself and ask a question.
Hi, my name is Larry Smith. This is, in a certain sense, I suppose, a follow-on to the first question tonight. Hi there. I was a little surprised that...
Stop that.
I was a little surprised that everything that everybody said was sort of, from my point of view, up here in the complexity level. And I'm more concerned about the very, very, very bottom. What is the universe actually made of at the most fundamental level we can imagine? And I know that, for example, string theory attempts that, but it's not background independent. It assumes the existence of space and time. And can we get a description of what space and time and mass and energy and so forth are? And I was just wondering if anybody on the panel has any comments about that.
Gee, how much time have you got? Because these guys could talk about it forever.
I can listen forever.
Yeah, maybe I can answer that. I mean, I think one of the profound new insights of the last 10 years has been the idea of holography, in which space and time, the three-dimensional space and time that we live in, appear to be equivalent to a two-dimensional space which lives on the boundary, a two-dimensional space which is the boundary of space and time, and in which you can apparently describe everything happening in 3 dimensions in an equivalent description which has only 2 dimensions. And so this is indeed moving in the direction of your question, that space is becoming less of a fundamental concept. There seems to be a simpler description, which involves one less dimension of space. Maybe this will go down to 0 dimensions of space. And we'll have space will just appear as another approximation of the world, not a fundamental thing at all.
But what about quantizing space and time?
So this approach of holography is the best approach we have currently to that problem. and it involves throwing away one dimension of space.
Sean, please.
Yeah, I think that Neil is exactly right, and I just wanted to do two things. First, correct a little bit, the statement, string theory assumes that there is space and time, because that's just not the truth. That is false. String theorists are very, very happy to show that two different versions of the theory actually look completely different from the point of view of space and time. And I think that this is a very, very interesting question just because space and time are two things we find it hard to live without or find it hard to contemplate without. But the lesson of quantum mechanics is that everything that we find it hard to live without, the position or the velocity of an object, are just things that appear to us when we look at things in certain ways. And ultimately, space and time are going to be the same way. It's the simplest, most conservative, least radical version of the right theory of everything is going to be one in which quantum mechanics is true. And the right way to think about the universe is as a wave function that tells us the different probability for different possible outcomes when we look at things. But that wave function will contain in it different possible ways that it can look like there's 3 dimensions around us, or it can look like there are 4 dimensions around us, or it can not look like that there are dimensions around us. And one of the obstacles, besides the fact that it's really hard to get experimental evidence one way or the other, is that it's hard to think that way. The reason why you think that string theory is wedded to space and time is because string theorists very, very often do think about approximate solutions to the theory where space and time are right there, and then they sort of poke at those approximate solutions a little bit because that's what we can do. That's what we can draw pictures of and think about and calculate things very easily. But when the final answer, if we get it anytime soon, comes to us, space and time will be things that appear to us just like the position and the velocity of a particle, not things that are right there in the fundamental description of nature.
Just to tell the audience a little bit in which interesting way we might disagree. There are people like me who believe that the wave function of the universe doesn't make sense because you always need a classical observer which is outside, whose information the wave function represents. And there's another message from the quantum important for space and time, which probably has not been really picked up yet, and that is, we heard the notion of entanglement before. The measurements on an entangled state, the measurement results, are completely independent of the relative arrangement of the measurements in space and time. You can have them space-like separate, you can have earlier, later, large distance, small distance. So in a sense, space and time don't matter. And that is very, very interesting, and it should be picked up at some point.
All right, I'm lost now. So you have a question.
Yes, my question relates back to your comment earlier, but that you felt that in the next 5-10 years we're going to measure gravity waves and other comments about quantum computing. So I'm thinking, just if you can imagine using quantum mechanics right now, just jump ahead 50 years. Imagine you're 50 years in the future. What are some of the major discoveries you envision we may have made, or what would the world be like 50 years from now?
Well, I think the point you were making was
wasn't
that
it Groucho Marx who said that? Wasn't it Groucho Marx who said it is very difficult to make predictions, and it's particularly difficult when they concern the future?
Exactly. I think it's really we do it, but it's really dangerous because we always miss the important stuff. And what I tell people is, if I knew what the exciting stuff was going to be, I'd be doing it now. So we don't have the slightest idea.
Foresee, or what discoveries do you think are imminent, and what current theories right now will have a major impact on our lives 50 years from now? I'm not saying this may be what happens, but what would you theorize could happen?
You seem to think, you guys seem to think that some of these issues that we've only discovered in the last 10-15 years are actually quite important.
No, the things we discovered in the last 10, 15 years are extremely important, but I think that the easier part of your question to answer, rather than what ideas will we have, is sort of what discoveries we can make, because it's becoming more and more a big science era where it takes decades to set up an experiment. And the good news is the next 10 years, even the next 50 years, are going to be fantastic for experimental results. We'll either detect gravitational waves or we won't, and if we don't, that's more exciting. We'll either discover the Higgs boson, or we won't, which is more exciting. We have very good chances of discovering supersymmetry, symmetry between elementary particles that we haven't yet found in nature, extra dimensions of space over and above the 3 that we live in, what the dark matter is, as Katie referred to, what the dark energy is, whether or not, what exactly happened at the first moments of the Big Bang reflected in the cosmic microwave background. So all of these are going to be happening and surprising us over the next 10 years. We're nowhere close to the point where it's just a matter of dotting I's and crossing T's anymore.
Gino.
Let me just give...
You're on.
Okay. Let me just give a quick answer. There's a famous mathematician, David Hilbert, and he said that if he was put to sleep for 100 years and then woken up, what would be his first question? His answer was, has anybody proved the Riemann hypothesis? So similarly, we were talking about having difficulty sleeping or what keeps us awake. If we were put to sleep for 50 years, I'd answer it differently. What would you like to know? My answer would be, it's a very conservative one. People say, well, maybe Einstein's equations are really right and you need a cosmological constant, and maybe that's what dark energy is. So I think I'd ask, is there a cosmological constant, and has anybody had a great idea for its magnitude? Which Larry is going to answer.
No, I just think we tend to be parochial because we're thinking about the present. All the questions that we've asked are ones that are of interest to us now. I suspect the important questions will be questions we don't even know we have. And in particular, lots of possibilities exist. It's possible that quantum mechanics may be shown to be not the right description of nature, for example. There's profound possibilities well beyond the things we've talked about within the context of the theoretical models we have now. And I suspect those will be the exciting questions of the future.
Ma'am, you have a question. No, please, go ahead.
Yeah, my name is Sandy Wang, and I have a zero background of the physics, so I dare to ask a very absurd question. And the question is that I read a lot of things about 2012, and it's interpreted a different way, but according to my understanding, it's our solar system gonna move into this photon belt, and that's going to cause a dramatic quantum leap of consciousness. So at the beginning, I thought this quantum to consciousness, that's actually quantum to cosmic. So my question is, from your super brain and this physics, in this technology, scientific way. And
what's going to happen in 2012, you're asking?
Yeah, what's your interpretation about that?
Anyone want to tackle that one?
Yeah, in 2012 there's going to be
a
presidential election. There's going to be you should stop worrying about 2012. All of the discussions of 2012 are complete and absolute nonsense. Don't worry about it. Nothing special is going to happen in 2012 except some interesting science and hopefully maybe some healthcare in my country or something like that.
Wouldn't it be fantastic if something really big did happen in 2012? Then we could,
Actually, I'm going to disagree slightly with Lawrence. You should worry about 2012, but not because of changes in consciousness, but we really got to get carbon under control. And every month that we leave it, it's getting worse and worse. And particularly coming from Australia, I have colleagues who are ocean scientists, barrier reef scientists, and things are changing now. Again, this is a little bit like the Darwinian debate. I think perhaps some parts of the world are a little bit behind than others, but that's something you should be worrying about for 2012.
Yeah. We'll just take another question from the web and then we'll go back to you, sir.
Emily from Toronto wants to know, if we can't really detect WIMPs very well, does it mean that the theory might be wrong? Do WIMPs really exist?
If WIMPs, with the WIMP detection, there's more than one candidate for the dark matter. If WIMPs aren't right, then there are other avenues that people are pursuing, axions, higher dimensional particles. There are a lot of different experimental venues that people are attacking right now. So my hope is that these experiments we're seeing right now that indicate that WIMPs are right, that this will actually be vindicated and verified over the next 5 or 10 years, And I think there's a very good chance of that. If that fails, then we go to plan B, plan C, and so forth. So this dark matter puzzle, I think, is on the verge of being solved, but there's a lot of different ways to attack it.
Katie's rooting for the WIMPs. Sir, you have a question?
Yes, I think this is for the director here at the Perimeter Institute. When you gave your talk, you mentioned something about an early universe where where the Big Bang could have happened in time. Would that separate time from space? And how would you define time in that?
There's a time-space continuum problem just now.
No, it's a much simpler notion that the Big Bang was an event in time. And in Einstein's description of the Big Bang, space disappears at that moment. Space shrinks down to zero size, and then the equations fail. But there are other descriptions, such as ones emerging from string theory, in which space doesn't have to shrink down to zero size. So space can still be there, time can still be there. What you have to do is modify the theory in certain ways, such that you can actually describe this moment. But all I'm saying is that there is the possibility of a much more conventional, if you like, conservative explanation of the Big Bang, which is that it was a violent event in a pre-existing universe.
Well, that's going to have to be the last question because we're going to have to wrap up, ladies and gentlemen. Can I say that we've covered a lot of ground, haven't we? From the very big to the very small, and my God, Leo, we even covered practical things and practical questions. Please join me in thanking our galaxy of physics stars.